Okay. Now let's see what happens as we increase the order of the polynomial. So as I said, we were cheating because we used a third order polynomial model, p equals 3, when we had generated the data from this red curve here, which is a third order polynomial. What happens if we use this model, theta 1 plus theta 2x? So here we have a polynomial, so p equals 2, and the order of the polynomial is p minus 1, which is 1. It's linear. Well, it's affine function. This is the linear part of it. Well, of course, we don't do very well. We're trying to approximate a cubic with a straight line. And the standard deviation I'm using in all of these cases is 5, by the way. So we don't do very well. What happens if we go cubic? Well, we know what happens. We've seen the result. We do pretty well. What happens if I use a 10th order polynomial? So here I'm using p equals 11. So the order of the polynomial is p minus 1 equals 10. So we're going theta 1 plus theta 2x plus all the way up to theta 11 x to the power 10. So we're using a high order polynomial to approximate this data that comes from a cubic. So the true relationship is this. The black squared dots are again the noisy points. And what is now our 10th order approximation? Well, we see this very wiggly curve here. And what is it doing? It's going right through the data points, almost. It's interpolating. So with this very expressive function, which can fit many different patterns, we see that we capture the points very well, but they're noisy, right? So we end up being very far away as we go from p equals p minus 1, the order of the polynomial, third degree polynomial, to 10th degree. We end up going further away from the true result. So let's now analyze what's happening here, because this is what will lead us to regression, with regularized regression. So this situation here, we call this underfitting. I'm going to try to make this more precise in a moment. This situation here we call overfitting. And I'm going to try to make that a bit more precise soon. But before I do that, we need to discuss model complexity. So what is model complexity, or as it's often referred to, model capacity? First of all, complexity and capacity refer to a hypothesis space. So a hypothesis space we're using is either first degree polynomial, third degree polynomials, or 10th degree polynomials. And what is it? It refers to the ability of functions in this hypothesis space, their capacity or ability to fit arbitrary patterns in the data. Now, for finite dimensional linear models, what do I mean by finite dimensional? I mean, in our case, we're looking at in linear regression models of the form f theta of x is equal to theta I, the sum over I, theta I, phi I of x. And we have a finite number of basis functions and therefore a finite number of parameters. And all functions f theta lie in our hypothesis space. And what is this hypothesis space? It's the span. It's linear combinations of a finite number of basis vectors. The span of var phi 1 up to the pth one, right? So we have a finite number of basis functions. And so this space is p-dimensional, where p is finite. So it's a finite dimensional space. It's constructed from the linear combination of only p basis functions. So it can have dimension at most p. Now, for such sorts of spaces, their capacity or complexity is controlled by the number of parameters, p. But this does not mean that model complexity is equal to parameter count, even in the finite dimensional case in general. Otherwise, deep learning wouldn't work, because in deep learning, we have a finite number of parameters, albeit very large, but complexity is not equal to the number of parameters that we have. What is complexity? Well, at this stage, all we can say is that parameter count is one way in which we can potentially increase complexity in some models, certainly in these linear models that we're using at the moment. So we can think of complexity or model capacity as an effective dimension. In infinite dimensional cases, meaning in non-parametric regression, we can have effectively an infinite number of parameters. We can simultaneously have a small model complexity, even though the number of parameters is infinite. And so this relationship completely breaks down. So what I'm saying is, in some cases, yes, there is a very close relationship between parameter count and complexity. And certainly in those cases, parameter count is one way to increase complexity, but it's not the only way to increase complexity. Rigorously, it's defined through what we call uniform deviations, which is something we will come to later when I discuss and define the decomposition of error in terms of approximation error and estimation error, and possibly also optimization error. And at that point, I will define what a uniform deviation is. And then we can, in terms of such a uniform deviation, define precisely what we mean by model complexity or a complexity measure. And this is where tools like VC dimension, entropy, Rademacher complexities, pseudo dimensions, and covering numbers come in. These are all tools that we use to try to measure the model complexity of a particular hypothesis class, and therefore try to bound the errors, usually the estimation error, in terms of this model complexity. So for the time being, what we're going to do is think of complexity, model complexity, as how much freedom a particular hypothesis class has to adapt to noise. So what do I mean by that? Well, if we look at the previous example, and we look at some noisy data like this, so this is data which contains quite a large degree of noise. What I mean is how much flexity a particular hypothesis class has to essentially find patterns that can fit this noise, go right through it, interpolate through these noisy data points. So in our case, in these linear models, something like this, an affine function, doesn't have much ability or capacity to do that. A quadratic has more capacity. A cubic has more capacity. A higher order polynomial, and the higher we go, has more capacity because it can fit all kinds of patterns, right? So this is why in this case, the number of parameters p in our linear models is one very good way to increase model complexity. So this going up means complexity goes up. So using this as an example makes things rather simple, but also perhaps a bit misleading, because this relationship, the parameter count equals complexity, is in general not true. And we will make this rigorous later on, but here we won't get bogged down in it too much. So to control complexity, what can we do? Well, essentially what we have to do is restrict our hypothesis class. We have to remove from it certain types of functions, which are perhaps too expressive or um, have too much ability to adapt to noise. So one way we can do that, one and only one way, is by restricting the sizes of the functions that we allow in our hypothesis class. So at the moment, we've been saying all functions such that this. Now what we are thinking of is all functions such as this, but also their size is restricted. And this type of restriction we call norm control. for reasons that will hopefully become apparent. So let's try to motivate it in our particular example. So what was going on? Well, we had a noisy data set and we were trying to fit polynomials to it. So we fitted an affine function, first order polynomial. We fitted a cubic and we fitted a 10th order polynomial. And these are the coefficients that we estimated in each case using our Moore-Penrose pseudo-inverse solution. So here I've also included quadratic and sixth order polynomial. Now notice what's happening. The coefficients in the theta hat that we come up with are getting larger as we increase the size of the polynomial. So here you can see we're starting to see some large coefficients. Once we get to 10, we're starting to see pretty large coefficients like this 25 almost here and this 27 here. The main thing is the sizes of the norms of the estimates that we are obtaining. So here's the norm of theta hat for the affine case, quadratic, cubic. Sixth order is now starting to increase. And by the time we get to 10th order, we see a pretty big jump in the norm of the theta that we estimated. So we got theta hat was equal to phi transpose phi inverse phi transpose y. So we're measuring the norm of this, the standard norm of this vector, right, that we got. This vector here. So what does this suggest? This suggests that we restrict the norm of our theta, the one that we obtain. So how can we do that? Well, we're going to have to go back to the beginning and adapt our problem such that this norm is restricted when we search for the solutions. Now, restricting this norm is the same as restricting the sizes, the norms of the function in our hypothesis space. So what I'm going to do is assume that we have a distribution for x. So we have some distribution. X is distributed according to some distribution p of x. I don't want to work with this, so I'm going to assume we have a density of this distribution px of x, little p x of x. So we can write everything, including expectations, in terms of this rather than integrals that involve integrating over this probability measure, right? So we need a norm. I'm going to define a norm for functions in f to see how restricting the norm of this is the same as restricting the norm of functions in f. So I'm going to use the natural norm. First, we have an inner product on the space of random variables given by this. So f, g, these are two random variables which are functions of the random element x. So we have f of x and g of x, and they're both real valued, so these are random variables. Functions of this random element, which are real valued, are going to be random variables. Now I'm going to define this as the integral of f of x, g of x, times the density of our random vector, or possibly variable if it's scalar valued, x, dx, dx. And this has an induced norm, right? So this inner product has an induced norm, f. So if I put f, g equals f here, and square root it, I get the norm of f, right? This norm is induced by this inner product. I'm going to label this the L2 norm, right? And to be precise, x has this density p of x, so I put p of x in here. And the square of this is therefore this inner product. So we're going to use this norm induced by this natural inner product that we have on this space of random variables. So let me reiterate that our f theta is a function of x, but we can also consider it a random variable if we have a random x, this random variable, because f theta is real valued. It takes possibly vectors in RD and maps them to real numbers. So it's real valued. So if this is random, its argument, then this becomes a random variable, it's real value. So we're going to assume this. So I'm going to define the norm. We're going to use this norm to measure the size of a function f theta, one of our hypotheses. And I'm going to give it this symbol. So the square of it is this integral, right, which is what I wrote down, f in a product of f with itself, which is also the expected value of the random variable f theta of x, the expectation of that squared. So this is one reason why we have this natural norm, and it's also this space with this inner product is a Hilbert space. So watch the videos on probability where all of this is explained, including the Hilbert space point of view. Okay, now what is our hypothesis? Well, it takes this form. F theta of x is the sum from I equals 1 up to p of theta I phi I of x. So f theta squared is going to be a double sum over I and j up to p of theta I, theta j. Now, what do we want to do? We want to square it. So this is now squared, this thing here. I'm going to put the phi's in a minute. Then we want to integrate it. But these are just constant. So, and we take the double sum outside. So we can put the integral here of the value space of x. Let me call that x. And here we've got the psi I of x times psi j of x times p x of x dx, which is what I have here. And the double sum and the thetas go outside. Now let me define a matrix G with components given by these integrals. Now, what are these integrals? These integrals are the expected value by definition of the ith component of the feature vector psi I of x, which is now a random vector, and the jth component of that random vector, of the random vector psi of x, which is psi 1 of x, psi 2 of x, up to psi p of x. So this is a random vector. And this is measuring the expected value of the ith, one of these, times the jth one, which is a correlation, an uncentered correlation, right? And according to the definition of our inner product, this is also equal to the inner product of psi I with psi j. So the ijth entry of this matrix G is given by this integral here. And we can write this whole thing, this norm, as theta transpose, the transpose of theta, times G times theta. If we want, we can write this as theta dot this, G times theta. So this will result in a vector, and we take the dot product of that with theta. So this is in matrix notation. Okay, so where next? Well, this G we call a gram matrix. It encodes, as I say, correlations between features of our feature map, this feature vector psi of, now we've got a random x. So this is going to become a random vector psi 1 of x up to psi p of x. So it encodes the correlations between the ith and jth components of this. Or we can call it, because it is the second moment matrix of this feature vector. Right? So let's not get too hung up on this right now. We'll come back to it much later. Now, if the basis is of orthonormal, so orthogonal and also normalized, so that each of these has unit norm, then this inner product, by definition of orthonormality, is the Kronecker delta, delta ij, meaning if I equals j, this inner product is 1. If I is not j, this inner product is 0. That's the definition of orthonormality. In which case, because this is the ijth component of G, if satisfies this relationship, then G must be the identity vector. And so what do we end up with? We end up with theta transpose identity vector, that's now our G, theta. Well, this disappears and we get theta dot theta. It's just the 2 norm of theta squared. We can put 2 there to make it absolutely clear. And so we have this relationship that the norm, using this natural norm, the L2 norm of our function f theta, is equal to the norm of theta squared. We might say, an isometric embedding. So now if G is not I, then this theta square, theta controlling this is still the same as controlling the norm of theta. But what we have is this is a ball. It's uniform in every direction. You can think of it as a sphere or a ball, whereas this norm would correspond to an ellipsoid. But this is enough for us now. Controlling this is going to be controlling the norm of f theta. And that's what we wanted to show here. So now that we've shown that, let me quickly mention the empirical version of this Gram matrix. It plays an important role in reproducing kernel Hilbert space theory. And so does the kernel, which is the sort of dual of this, where we are taking dot products. But that's something we'll come to much later when we study kernel learning. So if we treat the xi as fixed, so now we're not considering them as random, then we can replace the density with what is called an empirical measure, which I'm not going to define, and we get an empirical Gram matrix. So this is an empirical version of the integral that I wrote down on the previous slide. An empirical meaning based on observed data. And what is this? It is 1 over n phi transpose phi, where phi is our design matrix. So there are all sorts of lovely relationships here. And so this leads to an empirical norm of f, which is this quantity here. Now, it doesn't matter whether we're thinking of this or the actual one. The main point is that controlling the norm of theta is the same as controlling the norm of f. Okay, so that's what we wanted to show.